he has completed his PhD from Aligarh Muslim University in 1996 and has completed his MPhil during 1992. He has several publications to his credit. He is a member of many prestigious organizations like AMS, IMS, Indian Society for Technical Education, Ramanujan Mathematical Society, SSFA, Indian Science Congress, and the Vijnana Parishad of India. He has been an active researcher and has delivered many lectures in various international and national conferences. As a member of the organizing committee of several workshops and conferences around the world. So on behalf of SSFA and on behalf of the Department of Mathematics, University of Kerala, I welcome Ajay Shukla sir for chairing the session.
Thank you, Dilip. So, hello. Now, so I request Dr. Atul Dixit. He currently is with IIT Gandhinagar, and he's a very young, dynamic researcher, and his work is really, I think, a novel, basically, to actually the world. This, I think, very wonderful work carried out by him, and he did a PhD with Professor Bruce Bond. So I request Atul. So just you start now.
Yeah. Thank you, Dr. Shukla, for the kind words. Thank you, Dr. Dilip Kumar and Dr. Ahmad Ali for inviting me to give a talk at this ICSFA-2021 conference. Good morning, everyone. I will be talking today on external higher Herglotz functions. So let me share the screen. Is it visible?
Yes, sir, it is visible.
So this is joint work with my PhD students, Rajat Gupta and Rahul Kumar. So let me begin with what the Herglotz function is. The Herglotz function is defined in terms of this infinite series of psi of nx minus log nx divided by n. So it's defined for any x in the slit complex plane, and psi is the logarithmic derivative of gamma function. So sometimes this is called as digamma function. Now the thing to note is that if you look at the values of psi of x as x tends to infinity, then the first term in the asymptotic expansion is log x. And so when you have psi of nx, then if you subtract minus log nx from there, then what is the next term? That is big O of 1 by nx. And so along with this other n in the denominator, you will have absolute convergence of this series. So it is named after Gustav Herglotz, a Czech mathematician who worked in Germany at Leipzig. And it arises in Don Zagier's explicit form of the Kronecker limit formula for real quadratic fields. So here is a photograph of Gustav Herglotz. Actually, the function that Herglotz studied is slightly different from what Zagier encountered in his work on Kronecker limit formula. However, he named it after Herglotz. So sometimes it's also called as Herglotz-Zagier function. Very recently, in fact, 31st of December last year, Don Zagier here and his PhD student Danilo Radchenko, they both wrote a beautiful paper explaining arithmetic properties of the Herglotz function. So they related it with number of objects in mathematics, in particular in number theory. So for example, they related this function with Dedekind-Ita function. There were earlier functional equations satisfied by the Herglotz function that were found by Don Zagier in 1975 in a very influential paper. But this time they found many more functional equations which are in connection with Hecke operators on modular forms. Then they had cohomological aspects of f of x discussed in their papers, special values of these functions at rational numbers and at some certain quadratic units. So it's a very beautiful paper. I urge everybody to, a quite dense paper also. It's only 18 pages, but it really has a lot of things in there. So as I was saying, in 1975, Don Zagier worked on this function as he encountered it in his explicit form of Kronecker limit formula for real quadratic field. So it's actually coming from algebraic number theory, but it has beautiful analytic properties. So first functional equation that Zagier obtained was a three-term functional relation between f evaluated at x, f evaluated at x plus 1, and f evaluated at x over x plus 1. And he related this with dilogarithms and the special value f of 1, which is actually in terms of Euler's constant gamma and Stieltjes constant gamma sub 1. Okay, and he used them to prove a theorem of Mayer. There is another functional equation that he required that was relating f at x with f at 1 by x. And again, you have it in terms of explicit representation, in terms of some special values and logarithm function. So they are very useful apart from being intrinsically beautiful. Radchenko and Zagier recently used them to obtain asymptotic expansions of f as x tends to 0 as well as at x tends to 1. Why is it useful to find the asymptotic expansion for f of x as x tends to 0, for example? So as I showed you in the definition, we have psi of nx minus log nx over n. As x tends to infinity, the behavior of this function f of x is easy to obtain because of the behavior of this psi function that is known. But if you look at x tending to 0, then we have a problem, right? The psi function is gamma prime of x over gamma of x, and gamma has a pole at x is equal to 0. Log also is not defined at x is equal to 0. So in order to get the behavior of this whole function after summing this summand as an infinite series, it's not an easy thing. But now that we have this functional equation here relating f of x with f of 1 by x, suppose you want to know the behavior of f as x tends to 0. Here you get corresponding behavior of f as 1 by x tends to infinity. And that is same as f of x where x tends to infinity, right? That behavior I already showed you how it is. So in addition with this functional equation, we can readily get f as x tends to 0, how it behaves. So that's one application of this functional equation. If you look at this three-term functional equation, something like this occurs in diverse areas of mathematics, as diverse as, let's say, mass forms. When you look at period functions associated with mass forms, then cotangent sums, double zeta functions, etc. So for example, the period functions associated with mass forms are real analytic functions psi of x, which satisfy three-term recurrence relation. And here it is exactly the same arguments, x, x plus 1, and x over x plus 1. This is what you have here. There is some factor in front also that occurs when we have these periodic functions. But Don Zagier has a beautiful paper where he says about different functions satisfying three-term functional equations and how they are related in various areas of mathematics. So it's a beautiful paper. It's available on his website. Another beautiful thing that Radchenko and Zagier did in their paper was to relate this particular integral 0 to 1 log of 1 plus t to the power x over 1 plus t dt for any x greater than 0 with the Herglotz function. So anybody who looks at this integral at first glance might think that, okay, I mean, what's so special about this? So note that here x is in the exponent of t. Otherwise, this is an integral of elementary functions itself, right? But there were no evaluation of this before Herglotz. And Herglotz actually did it using techniques from algebraic number theory, as I'll later on explain in detail more. But last year was the first paper by Radchenko and Zagier where they actually use analytic means. And now you can tackle this integral by means of analytic means, because this j is related to the Herglotz function, three Herglotz functions, or Herglotz function at three different arguments that you have to consider together. So f at 2x, then f at x, and f at x over 2. And using this, they were able to find the special values of j at rational numbers. For example, at x is equal to 2 over 5, you have this. At x equal to certain quadratic units. Now, if you have 4 plus root 17, this is how it looks, the evaluation of this integral. So earlier, as I said, this is the paper of Herglotz where he evaluated it for something like 4 plus square root of 15. And this thing was generalized by Muzaffar and Williams for evaluating it at x of a particular quadratic unit, like n plus square root of n square minus 1. So this is of that form, 4 plus root 15. But look at the previous page, it's 4 plus root 17. So something of that kind was not something which would be tackled by these techniques in algebraic number theory. But now this analytic means actually allows us to evaluate not only at other quadratic units other than the ones of this form, but also at rational numbers. So that's a beautiful thing. So there is a statement by Sarvadaman Chawla regarding this integral evaluation by Herglotz. He says that a direct evaluation of this definite integral is probably difficult. Since Herglotz's paper came in 1923, there haven't been any elementary evaluations of this. And even the paper that appeared last year has to have this theory of Herglotz functions employed in order to get to the evaluations at various values. So I urge any calculus students who are curious to solve various integrals to try to tackle this. Maybe somebody comes up with an elementary method to evaluate it, and that will be wonderful. Anyway, so this was regarding these Herglotz functions. There have been various generalizations of Herglotz functions in the literature. So Ishibashi in 2003, he studied a generalization. He called it as jth order Herglotz function. How is it defined? So Rj of x is a generalization of a function R of x that was studied by Christopher Denninger. I'm not going to really discuss this R of x, but it's the case when j is equal to 2. But how is it Rj of x defined? It is defined as a solution to this difference equation, satisfying this initial condition. Okay. So what happens when j is equal to 1? It's easy to look at it. R1 of x will be solution of this difference equation, f of x plus 1 minus f of x is log of x. In this particular case, I'm sure many people must have recognized what is the form of f of x. It is log gamma of x. Because if you look at log gamma x plus 1 minus log gamma x, what does it give us? Log of gamma x plus 1 by gamma x. Use the functional equation for gamma function. Gamma x plus 1 is x gamma x. So it's x gamma x over gamma x inside the log. So gamma x cancel and you have log x, which is what the right hand side is. Okay, and you can also check that the initial condition is also satisfied. So R1 of x is nothing but log gamma x. Now here you are taking its derivative. So what is the derivative of log gamma x? That is nothing but the digamma function, psi of x. So with x replaced by nx, it is psi of nx minus log nx divided by n. That is precisely our Herglotz function, isn't it? So when j is equal to 1, this is the Herglotz function. And Ishibashi encountered a generalization of that for any natural number j while trying to obtain the Lorentz series coefficients of this zeta function associated with indefinite quadratic forms. Earlier, Zagier had counted only, or Zagier had evaluated only the constant term in the Lorentz series expansion, as well as the coefficient of the singular part, 1 over x minus 1, because there is a pole as is equal to 1. But now all of the next coefficients, which are analogous to the Stieltjes constants, were evaluated by Ishibashi, and that's where he encountered this generalization. Riyad Masri actually has another generalization where he has a periodic function here, alpha of n, and also he puts n to the power s. Now s is any complex number such that real part of s is greater than 0. Vlasenko and Zagier, in an influential paper in Krela, they further looked at a special case of this Masri's function, which is, now you don't see log nx here because that's not really required for convergence. Okay, when k is strictly greater than 1, you don't require this log. But when k is equal to 1, this series will diverge, and that's why you require this log nx to be subtracted. So they looked at this generalization of Herglotz function. They called it as higher Herglotz function, and they encountered it in higher Kronecker limit formulas for real quadratic fields. Here is a photograph of Riyad Masri, and here is Masha Vlasenko. So Vlasenko and Zagier in their paper obtained corresponding functional equations for fk of x. One is relating x with 1 by x, right? And the other is the 3-term functional equation. Here it's you have a multiple zeta function. Now, in our work with Rajat and Rahul, we looked at a different generalization of higher Herglotz functions or Herglotz function that we call as extended higher Herglotz function, EHHF. It is defined in this way. What you do is you have this parameter n that you put in the exponent of n. And as long as you have k and n which are positive real numbers such that their addition is greater than 1, the series is convergent for any x in the slit complex plane. We encountered this from our prior work on generalized Lambert series. So one thing that is required is you can easily look at various generalizations very easily. So when you put this in terms of, when you split that for k greater than 1, you can do that. Then this series can be easily evaluated in terms of zeta of k and zeta prime of k. And then the resulting function is a generalization of the higher Herlotz function. If you put n equal to 1, you get a higher Herlotz function. But if you put k and n both equal to 1, then you are back to Herlotz function of Zagier. Okay, so this is what I have said here. The one thing that so we don't really require this log term when k is greater than 1, but we wanted to put all of these generalizations that are all of the previous considerations under one single roof. That's why we took this log. The motivation came from our work on generalized Lambert series. For example, let me go with this generalization of one formula of Ramanujan. This is a talk celebrating this National Mathematics Week, so there ought to be a mention of Ramanujan. Here is a very beautiful formula of Ramanujan for odd zeta values. So it's a beautiful, almost modular relation involving this expression for alpha related with this expression with beta, and the modularity is obstructed by means of this particular finite sum involving Bernoulli numbers. So why is it important? Because it encodes many important properties of Eisenstein series on SL2Z and their Eichler integrals. So for example, if I take m, see, this is valid for any non-zero integer m. If I take m to be negative integer less than -1, for example, -2, -3, -4, so on. Let's say m is -2. Then what do you get here? You get n cube. That is what we get in the Eisenstein series E4, or in Ramanujan's notation, the Eisenstein series cube. And you see that then it gives a perfectly modular relation. Why? Because when m is -2, this is just vanishes. This vanishes. If you take m is equal to -1, you get the transformation formula for quasi-modular form E2, or in Ramanujan's notation P. Because why quasi-modular form and not modular form? Because when m is -1, there is one term in here, j equal to 0 term. And similarly, you can get the transformations for Eichler integrals, for Dirac and eta function, etc. So what we did a few years back, the paper came last year, was with Gupta, Kumar, and Maji. So we gave a two-variable generalization of Ramanujan's formula, or in other words, I should say one variable and one parameter generalization. The variable is a, where a is between 0 and 1, and n is an odd number, and alpha, beta are positive such that they satisfy this relation. Now, if you put n is equal to 1 and a is equal to 1, then you will get Ramanujan's formula. So in a way, this is a two-variable generalization. And that's where if you look at the other side, on the right-hand side, we have this generalized Herlotz function coming into picture. So that's what motivated us to work on this. So similar to what you have here in Ramanujan's formula, we were able to obtain a very nice result involving these Herlotz functions, or I should say higher Herlotz functions of Lasenko and Zagier. Very similar symmetry you have. On one side, you have this alpha, on the other side, you have beta, and then you have a finite sum. But note that in Ramanujan's case, you had even indexed Bernoulli numbers, which are related to zeta values at even arguments. Here you have zeta values at odd arguments, as you can see here. Now, one may say that, okay, Lasenko and Zagier have these functions, functional relation for their functions. So what you take one of these, what if you take one of these with argument I times alpha over 2 pi, and then another with minus I alpha over 2 pi, and then add those? Aren't you getting what you have here? So the answer is no, because they have certain things certain factors in front of their functional equations which do not really work out. So this cannot be obtained using Lasenko and Zagier's work. What we did was we even generalized this to the case of capital N, like occurring in the exponent of n. But let me give one special case, which is really nice. When you have m is equal to 1, this term vanishes, right? J going from 1 to 0, and you have a perfectly modular relation. involving zeta of 3. Okay, so we generalize our further work here, this transformation, by having further generalization. So let me go over this notation. This means that you're summing certain thing over j equal to minus of n minus 1, minus of n minus 3, minus of n minus 5, so on, up to n minus 3, n minus 1. Okay, so you're skipping intermediate things. So that's why you have this double dash. So here is our first functional equation, where you have this addition of two extended higher Helmholtz functions. If you put here n is equal to 1, and then specialize x to be in terms of alpha, and then use the relation alpha beta equal to 4 pi square, then you'll be led to this particular special case that we found. So just to make sure, Professor Shukla, I have 8 more minutes, right? I started around 10:05 or 10:06. So I have until 10:35, isn't it? 8 to 9 more minutes.
Yes, sir. Yes, yes.
Thank you.
Yeah, you can take.
Okay, thank you. So this is the first functional equation. This any special case of this was also not considered by the previous people, like Zagier or Vlasenko-Zagier or Radchenko or Zagier, Mastri. Nobody actually really did with the addition of these two functions. Okay, this came. I'll go over the proof or the ingredients of the proof. This came through our work on generalized Lambert series very naturally. But we also have this other type of functional equation, which reduces to the functional equation of Zagier when you put k and n both be equal to 1. Okay, for example, if you let k and n both be equal to 1, f(1,1) of x is nothing but that f of x of Zagier. When you put n is equal to 1, the only term that you have to consider here is j equal to 0. When you have j equal to 0, note that here you have 1, n is 1, so you have 1 by x. And if you put k and n also as 1, you again get f of 1, 1 of 1 by x. So there comes the relation between f of x and f of 1 by x that I showed you previously. Okay, one has to work out really, but one can actually prove it. Okay, so for k is equal to 1, but n, any general, you have a different type of relation. I mean, the form is same, just that the residual terms have to be counted because there is a contribution of pole of higher order that one has to calculate. Okay, so as I said, in here, if you put n is equal to 1, then this is what you are going to get. This is the relation of Zagier. Okay, so if I come back to this first functional equation, what is the ingredients that one really use? This is an important closed form evaluation coming from our previous work with Gupta, Kumar, and Maji. So it's a delicate result in the sense that this series is not absolutely convergent. If you interchange the order of summation and integration, it will be divergent. Yet it has this beautiful closed form evaluation involving psi function, and that's where you see the connection with the Helmholtz functions. And one more inverse Mellin transform representation. Okay, why are these extended higher Helmholtz function or their functional equations important? They can be used to calculate asymptotic expansions not only of themselves, but also of generalized Lambert series. So here is one such. So for extended higher Helmholtz function fk, n of x, where k and n satisfy these conditions, if you are letting x tend to 0, this is the full asymptotic expansion that one gets using these functional equations. So you have this main term consisting of 1 by x, then log x, then you have this constant term, then powers of x, and then the error term part consisting of this infinite sum. For k being equal to 1, one has to go separately because the functional equation has separate residual terms. And then one recovers the relations of Radchenko and Zagier, asymptotic expansions of them when n is equal to 1. We have also separate asymptotic expansions when you have sum of these two functions. Note that the two functional equations are completely different. They only match in a certain special case, special values of k and n, but otherwise these two functional equations that I have shown are completely different. Let me also go over one transformation of a generalized Lambert series. So this formula I already showed you before. It has this A and capital N, and when both of them are equal to 1, then this gives us Ramanujan's famous formula. But now you have a real valued parameter, right? A. So differentiation is possible. If you differentiate both sides with respect to a and then let a be equal to 1, you get a really nice result, which is here. Again, sum of two extended higher Helmholtz functions is what you see here. I mean, the log term is not there, but you can always add and subtract. And then for m greater than or equal to 1, you always have the convergence of the series log n over n to the power 2. Okay, so that's not a problem. When you further go and put n is equal to 1, you get a formula which I recently established, I mean last year, with Ashita Kesarmani and Rahul Kumar, which is what is called as a companion, which could be called as a companion to Ramanujan's formula. Because in Ramanujan's formula, if you look at the left-hand side, there is alpha to the minus m, zeta 2m plus 1, and then 2m plus 1 here. I mean, minus of 2m minus 1. So it's like in here, if you replace n by m plus half, you'll get Ramanujan's formula left-hand side of that. But right-hand side of Ramanujan's formula also has a Lambert series, which is not the case in here. You have this higher Helmholtz functions which come into picture. Okay, so that's a beautiful formula again that you can get as a special case using a more general result. And now with the help of these asymptotic expansions of the higher Helmholtz functions, one is able to give asymptotic expansion of this Lambert series, which was not previously possible. Complete asymptotic expansion as alpha tends to 0. This is how it looks. One more thing which is really very nice, and I would like to comment on that, is that a polylogarithm function, many people know, it's defined by summation t to the n over n to the power s. They have applications in several areas of mathematics, like computing volumes of hyperbolic 3 manifolds, then special values of Dedekind zeta function at s is equal to 2, algebraic K theory of number fields, etc. So we encountered a new generalization of polylogarithm where we had this t to the n to the power capital N over n to the power s. And using this, we were able to generalize the Radchenko-Zagier relation between this integral and the Helmholtz functions. And it looks like this. So here is where the generalized polylogarithm appears, but you have exactly a similar form in a more generalized version. You have in Zagier's case, or Radchenko-Zagier's case, they had three functions, f of 2x, f of x, and f of x over 2. If you put capital N equal to 1, that is what you have. So this is a nice generalization. We actually used it in order to calculate almost closed form representation of this integral involving the dilogarithm function. This is how it looks. Why do I say almost closed form and not a closed form itself? Because the only unknown thing of which we don't have an explicit closed form evaluation is this f sub k of 2, which is this series. Otherwise, all of them is in terms of the special values of zeta function. It's a nice results that one can get. Okay, let me conclude in 2 minutes. We do not have a generalization of this 3-term functional equation of Zagier. So we really worked for about 2 to 3 months on getting this. Unfortunately, we couldn't, but there are some ideas that we have as to how such a generalization would look if at all it exists. And unfortunately, I don't have time to go in details, but let me say just this thing, that these three Helmholtz functions will be replaced by these ones. I mean, this is what we feel. And we have evidence for this for justifying this, which is what I have in these 2-3 slides. Unfortunately, I don't have time to go over it, but these will look like this. So when you put capital N equal to 1, you recover the 3 ones that occur in the, and also when k is equal to 1, x, 1 plus x, and x over 1 plus x. This is what you had in Zagier's relation. Anyway, so another beautiful thing, I would like to end with this talk with the Formula of Ramanujan. So in the last notebook, on page 220, he works with infinite series involving this lambda function. Lambda is nothing but in terms of this psi function, the digamma function, and the 2 terms here, 1 by 2x and minus log x, which are obtained from the asymptotic expansion of psi of x. So if you subtract the first 2 terms in the asymptotic expansion of psi of x from psi of x, then those are precisely these 2 terms. And that's what makes this series absolutely convergent, because this summand is something like big O of 1 by n squared. Then Ramanujan takes these residual terms involving Euler's constant, multiplies the thing by root alpha, and then has a beautiful property that f of alpha is equal to f of beta, where alpha and beta are such that alpha times beta is 1. This is a modular relation. In modular forms, you have z going into minus 1 by z. This is an analog of it. Equivalent to alpha going into 1 by alpha is that z going into minus 1 by z. And not only that, both expressions are equal to this particular integral involving the generalized, or sorry, the completed Riemann zeta function. Unfortunately, again, I don't have time to go over it. But we really think that this lies in the realms of the theory of Herglot's functions. Why? Because you are summing something like psi minus log in here. You have an extra term because you don't have anything in the denominator over n. Okay. If you don't have anything in the denominator, you must take the second term also, otherwise the series will diverge. So we really think one should be able to obtain this relation of Ramanujan using the theory of Herglot's functions. So I think I'm running out of time. Let me just skip these things and stop here. Thank you very much.
Thank you, Dr. Atul Dikshit. Really, this is very wonderful talk.
Thank you.
And I request the audience, if you have any query, they can ask from Atul. Okay, so there are no query. Thank you, Atul.
Thank you. Thanks a lot. Just a moment, I'll try to. Yeah. Okay. Thank you.
Thank you, Atul sir, for your nice presentation. It was really nice hearing your talk, and congratulations for your achievement this year.
Thank you, sir. Thanks. Thank you so much.
Thank you. Ajay sir, are you there?
Yeah. So I request, now I request Professor Subi Khan. She's professor of mathematics at Aligarh Muslim University, and she is very dynamic lady, and the field of administration as well as the academic life, and a lot of good number of paper credit to her, and many students have completed their PhD. His or PhD under her supervision. So I request Professor Subi Khan to deliver his talk.
Thank you, Dr. Ajay Shukla. And once again, I extend my thanks to Dr. Dilip Kumar, Dr. Ahmed Ali, and other dignitaries of Society for Special Functions and their applications for providing me an opportunity to interact with such an audience and giving me a chance to deliver my lecture here. And we have to start thinking about like recently also I delivered a lecture on Lie algebraic techniques. So as we all know that the concept related to special functions previously was that it is something in which we just go on doing computations, but there are certain recent research work going in this direction, which are proving that this is just not mere computation, but there are so many things, and of course its relation with applicable analysis and function analysis, approximation theory, operator theory, and whatnot, geometric properties, etc., is making it more and more wide. So in my talk, I try to give an idea of relating the special function with Lie algebra, and then also I try to show that if we want to relate the quantum calculus or quantum algebra, then for that we will be going to take the basic analogues of special functions, or we sometimes refer to them as Q special functions. So because I think I have half an hour time, so I may be becoming a bit faster in my presentation. So just to give you an idea of both the techniques, that how they work and how we switch from the ordinary Lie algebra relation of Lie algebra with the special functions to the relation of Q special functions with quantum calculus. So is my screen visible? Everything is okay?
Yes, ma'am.
Okay, okay.
It's visible.
You are able to see the screen?
Yeah.
Okay. So as I mentioned, we will be going to see how we proceed from Lie algebraic approach to two-dimensional Hermite polynomials to the same approach to two-dimensional Q Bessel functions. So here I have chosen two functions. One is ordinary, but it is of course the two-dimensional Hermite polynomials, and the other is again 2D, but it is Q Bessel functions. So when we move from if I just want to give an emphasis about the thing which we have taken here, and just to give a brief introduction about the things, if we look at the theory of group representations and its relations to special functions, it's quite old, and we followed WJR Junior Miller books to see or to learn these things, that how we can relate the Lie theory with the special functions. So the theory of group representations and its relation to special functions, it provides a powerful tool to the development of mathematical physics, and that makes it more interesting. And if we look at special functions, then we observe that they appear as basis vectors and matrix elements. That we will be going to relate them to local multiplier representation of Lie groups. And now if we, as in this talk, I just want to relate the theory of Q special functions. So this has found a group theoretic interpretation using the techniques of quantum groups and quantum algebras. So the quantum algebras provide a natural algebraic setting, of course, for Q special functions. So the theory of quantum groups and quantum algebra has enriched the theory of Q series, and it is in much the same way as the Lie theory has brought richness to the theory of ordinary special functions. And that is my aim to show in this talk. That is how we can see that we move from 2D special functions relation with harmonic oscillator Lie algebra to the 2D Q Bessel functions with the relation to the harmonic oscillator with the, another algebra, that is Euclidean quantum algebra EQ2. So we will be going to see the results for the two-dimensional Hermite polynomials, and we will be going to see how we have established these results by using the representation theory of the harmonic oscillator Lie group. And for the 2D Q Bessel functions we have taken, and we frame them within the context of the representation of a Q algebra, and that is namely the two-dimensional Euclidean quantum algebra EQ2. And of course, this is going to give us the results for these functions which we have taken. The contents of this talk, which I am giving here, are based on the following joint papers of with my research students. One is published in Integral Transforms and Special Functions in 2017, and the other one is published in Reports on Mathematical Physics in 2019. So just to see which polynomials we have taken the two-dimensional Hermite polynomials, and they were introduced by Ismail and Zell in 2015, and they were defined by this series, these polynomials, and we, just because there is a parameter beta, so they are named as one parameter two-dimensional Hermite polynomials. And then there are certain interesting properties which make them special, and that is their relation with the two-dimensional Hermite polynomials, relations with the 2D Hermite polynomials, and also with the Laguerre polynomials. Okay, this is not two variable Laguerre. This is the product of two variables here. So you can see that this is the two-dimensional Hermite, and it is related with the Laguerre polynomials with the product of two variables. So again, if we add to add an essence, we have the orthogonality property also for these polynomials, and this make them more interesting, and we can think about their applications in physics and in other fields also. And then for our purpose, we need that we should be having some regress relations, because these are the relations which help us in determining the operators, which finally we will be going to see how we are going to relate them with the corresponding groups or Lie algebras. So these are the recurrence relations. Now, in view of these recurrence relations and the orthogonality property, as I mentioned, we find them they are suitable for our purpose, and we can frame them within the context of the representation of the harmonic oscillator Lie algebra G01. Again, as I mentioned, that the theory of group representations and its relation to special functions, it is giving us a powerful tool to the development of mathematical physics. And this is the book which I mentioned, that is the Miller book. The harmonic oscillator Lie group we have taken here, to which we are going to relate the two-dimensional, one-parameter two-dimensional Hermite polynomials. So this is a 4x4 matrix form defined, and the group operation is of course the matrix multiplication. And when we have a Lie group, we have to consider the corresponding Lie algebra as well. So the corresponding Lie algebra for this we denoted by a different type of G, and this is again the 4x4 matrix form. And of course, the operation here is now the Lie product. This is the commutator relation. So the elements of the Lie algebra, we will be making them act with this commutation relation. Again, the interesting thing which we require is the basis elements. So these are the matrices, 4x4 matrices, which work for the basis, forming the basis for the Lie algebra. And another interesting thing which is helping us to relate these with the special function is that they have specific relations, commutation relations, and these are the commutation relations satisfied by these basis elements. Now, to give an idea about the Q calculus, it has started to appear in the 19th century because of its applications in numerous fields of mathematics, physics and engineering. And the quantum calculus has been recently named in comparison to differential or integral calculus. So in Q calculus, the Q analogs of mathematical objects are investigated. And basically, I think most of the audience know about the Q special functions. It happens that if we take the original, if we take the limit tending, limit of Q tending to 1, then we reach to the original object. The recent interest in the subject with the history beginning in the 19th century is due to the fact that Q series has emerged in so many diverse areas, such as statistical mechanics, quantum groups, and transcendental number theory also. So these are some basic concepts related to the Q analogs, or rather we should say that when we are going to switch to define the Q special functions, then of course the notations which we were using for the special functions, we have to look for their Q analogs as well. So these are the basic relations, Q shifted factorials, Q analogs of the shifted factorial, and then the this is the Q analog of a complex number, then the factorial functions Q analog. So all these basic things are there, and then the Gauss Q binomial coefficient is given by this thing, and then of course the Q analog of this function x plus y power n. n. So these are just the basic things. And the interesting thing I found here is that we have here two exponentials, then the Q analogs of exponential functions. So this is quite a query for me also. So like this one is denoted by small e and the other one is with capital E, and of course they are related by these type of relations. So these functions, of course, now when you have to handle with the concepts, then we will be going for the operations as well. So this is the derivative properties for both exponential functions. It is different, and also the Q difference operator we will be defining by this relation. And when we have to handle with the derivatives, then we will be going to see the product rule also. So this is the product rule which we follow when we have to deal with the Q derivatives for the product of two functions. And now the polynomial which we will be going to consider here, rather the function I should say, that is Q Bessel functions. This is defined in terms of the two exponentials, that is summation n equal to minus infinity to infinity j n x q t power n, and here these are two exponentials with the small e. And this is the series expansion of the Q Bessel function. This is defined by this thing, and the condition for this series is that it converges absolutely in the disk mod x less than 2. And this is the property which we can see is analogous to the property for the ordinary Bessel function, that is for j minus n, it is minus 1 power n. And there is another interesting relation of the Q Bessel function with the hypergeometric representative hypergeometric function 2 psi 1. This is in this form. And now generating function, we have taken another Bessel function. This we called as the second kind, and we have denoted it with the this 2 here, and this is defined by the two exponentials with capital E. And now we have this series expansion for this Q Bessel functions, and also this relation, and this is the hypergeometric representation for the Q Bessel function of the second kind. This is a generating function for the generalized Q-Hermite polynomials, because we will be going to have some relations between these Q-Hermite polynomials also. And this is the series expansion of the generalized Q-Hermite polynomials. Now, let's come to the main thing, that is how we will be going to relate the Lie algebra or Lie algebras with the special functions. So here in the first part, I have taken the harmonic oscillator Lie algebra G01, and we are going to relate it with the polynomial which we have taken, that is the two-dimensional Hermite polynomials. So here we have taken this irreducible representation of the Lie algebra G01, and this is defined for each omega mu belongs to C such that mu is not equal to 0, and the set of eigenvalues of this representation is given by minus omega plus k for k as a non-negative integer. And then of course we will be going for the basis for this representation space, and this basis is having these properties here. Here you have seen this complex constant omega. So this is basically, just a second please. This complex constant I'm sorry, there are certain disturbance. I'm doing it from my home. So this complex constant omega is become irrelevant, and so we choose it according to our convenience. And here we have taken omega equal to beta, and also there is no loss of generality for special function theory if we take mu equal to 1. Now these operators j plus j minus j3e satisfy the following commutation relations, and it is interesting to observe that these relations are same as the relations satisfied by the basis elements of the harmonic oscillator Lie algebra. So now, what next? In order to derive the implicit formulae involving the one parameter two-dimensional Hermite polynomial, we will be going to find the differential operators, and for that we will be going to use this eigenfunctions should be of this form. And now the work is started, and we find the operators. Operators should be such that they should satisfy these relations. And also we will be going to see that they should be satisfying many more relations also, that is these things. So these operators satisfy commutation relations 41, and they are defined on the space of all functions which are analytic in the neighborhood of this point. So now next to find the realization of this representation, because we have chosen omega equal to beta and mu equal to 1. So we will be going to see that these are the relations satisfied by these, and these are the relations which are stressing that they are related with the harmonic oscillator Lie algebra, and not only with harmonic oscillator Lie algebra, with a specific type of representation of the harmonic oscillator Lie algebra. So that is the point where we say that these are the polynomials which are the solution of these equations, and therefore we can claim that we can choose ym and z1 z2. We have taken two indices here. There is an interesting story about taking two indices also, because in Miller's book or in everywhere, most of the work have been done on especially with functions or polynomials with one index only. And when we have come across with some functions where we were dealing with, or where we come across with two indices, then there was a natural question that how we can relate them with representation theory, or what we will do with, or how to deal with the two indices simultaneously. Then fortunately we have got an idea that we can do one thing, that when we do the relation of the special function with a representation, and then we can fix the other index. So this has come out very interesting. That is, when we fixed the index n, we notice that this is related with the representation upper headed beta 1 of G01. So these are all the computations here. And then we have got the multiplier representation expression, and this is the final expression. And when we substitute the multiplier representation expression here, we will be having this type of thing. And now we calculate the matrix elements, and we write them in the convenient form in this way, where these functions are the associated Lagrange polynomials. So we have got the expression for the matrix elements, and finally by substituting this in the expression of the multiplier representation, this is the implicit summation formula for the one parameter two-dimensional Hermite polynomials. As I mentioned, when we have related it with the upper headed beta 1 representation of the harmonic oscillator Lie algebra, we have fixed the index n. Okay, and then there are certain special cases which we have taken. So these are all the special cases. I'm not going into the details, just takes some suitable substitutions, and using some limits, we will be going to get the particular cases of these formula which we have got for the same polynomial, that is for one parameter two dimension, and we may call them as the identities also for this. Now, again, we noticed that when we fix the index m and we work with n, we interestingly observe that this polynomial is now related with another representation of the same Lie algebra, and that we have done. And here in this situation, the choice for omega and mu is like open to us. So here we have taken omega 0 and mu equal to 1, and that way we found these type of operators, and we observe that they are satisfying the commutation relations, which are the commutation relations of the basis elements for the Lie algebra G01. So here again, we proceed in the same way. So I'm not going to repeat all these things. The different representation with the different index has given us different results. And we have got again some particular cases we have taken by taking or by making use of the limiting cases for C0 and B0. And these are the results for particular cases. And now there are certain examples also. When we take beta equal to 0, we are getting the results for two-dimensional Hermite polynomials, because we have shown that one parameter 2D Hermite is related to this polynomial also. And also these are certain examples which follow by taking particular values, of course, the suitable ones. And then we have derived the implicit formulae involving the Laguerre polynomials by making use of the expression of the polynomials. And then these are all those results which we obtained. And now, in the second part of my talk, I want to give the emphasis, that is, I want to give the emphasis that how we will be going to take the 2DQ Bessel functions. So the importance of Lie groups and Lie algebras is well known for the study of orthogonal polynomials and special functions. And if we, I mentioned it earlier also, that is the presence of quantum groups and generalized universal enveloping algebra that are known as quantum algebras, and evolution of their representations led to their applications for getting the properties of Q orthogonal polynomials and Q special functions. So the theory of quantum groups and quantum algebras has enriched the theory of Q series in the same way. This is again, I am repeating, as a Lie theory brought richness to the theory of ordinary special functions. So here I try to give you certain quantum algebras and associated Q special functions, which are well known. So the relationship between quantum algebras and Q special functions, this we have taken just to see how it can provide insight into Q special function theory. So like you can see the Euclidean quantum algebra EQ2, which we are taking here, is going to relate, we are going to relate with Q Bessel functions. Then Q oscillator algebra SUQ11, it may be related to Q Laguerre polynomials and Q Laguerre functions and polynomials, Q Hermite polynomials and Q Gegenbar polynomials. Some work has been done, but this we are trying to relate with, we are trying to get some other relations of some other Q special functions with some other quantum algebras. And then quantum algebra SLQ2C is related to Q hypergeometric functions and Q Jacobi polynomials. So 2D Q Bessel function we have taken in this form, and now you can see the product of two exponential functions with a small e and two exponential functions with capital E, and the variable x is associated with this small and the variable y is associated with the capital EQ. So this is the generating function, and this is the series form. We have three series here for 2D Q Bessel function. This is defined by, and now we come to the algebra with which we are going to relate it, and that is the two-dimensional Euclidean quantum algebra EQ2. This is determined by its generators H, E plus and E minus. So these are the generators, and these generators or these operators satisfy these relations, these commutation relations. And now here again, as I mentioned, that we will be going to consider the representation of the quantum algebra EQ2. So the irreducible representation omega of EQ2 is characterized by the positive number omega. Okay, and now the spectrum of this operator H, which is corresponding to this positive number omega, this is the set of integers Z and complex representation space has basis factors Fj, J belongs to Z such that these relations are also satisfied. That is, if we take the action of E plus minus 1 on Fj, it is giving us omega Fj plus 1 in the same way as we have taken in the case of harmonic oscillator Lie algebra with two-dimensional Hermite polynomials. And here also this is an invariant operator. Sometimes this is also known as the Casimir operator in the case of ordinary Lie algebras. Now, a simple realization of omega is given by these operators. That is, we are taking them in terms of single variable z. So h is zd upon dz, e plus is wz, and e minus is w upon z. And these are acting on the space of all linear combinations of the function z power j. Here we have taken simply the monomial, that is z power j, and z is a complex variable. And j is belonging to the set of integers, and the basis vectors here are fjz is equal to z power l. Now the question is how we are going to move from this monomial to the function which we want to consider, that is to this function, the two variable 2D Q Bessel functions. So let's see how it works. So we will be going to take the matrix element Tsj of the complex motion group in the representation W, and this is defined by this. Now we have got the like the multiplier representations.
My request to kindly conclude it within the 5 minutes.
Okay. So in view of this model, the following Q analog of the matrix elements are obtained. So these are all the computations. So just I would like to give you the main result here. That is the following generating equation involving the product of Q Bessel functions of the first and second kinds respectively hold. So these we obtain for the two-dimensional Q Bessel function here. For this we have used the quantum algebra EQ2 and the representation W. For the 2D Q Bessel functions, we have got the explicit summation formula, and we notice that this explicit summation formula comes in terms of the single variable Q function here and here again. This is for X and this is for Y, and here we have the two variable Q Bessel functions or 2D Q Bessel functions. They also satisfy the Q difference translations in the same way as we have observed for the ordinary special functions. And then they are, we also prove these functional identities for the 2D Q Bessel function. These are all the identities which we have established. And then we have got the result for the Q generalized Hermite Bessel function also. That is, we have gone to the to a hybrid family also. And this is expressed in terms of like h nu n plus 2k x by 2q, and here we are having Hermite Bessel functions, Q Hermite Bessel function. So these are two relations for this also. And again, if we try to give an explicit expression for the generalized Q Hermite Bessel function, which is given in this form. And then this is for the Q Hermite Bessel functions. We have the hypergeometric representation also. This is making our results more applicable and I should say maybe more important. And these are the results for the Q Hermite Bessel functions. And after some replacements, we will be getting the results for Q Hermite Bessel function. This we will be having or we will be claiming it to be the generating function for the generalized Q Hermite Bessel functions. And again, we will be going for differentiation, and we are going to get the this relation for differential relation for the Q Hermite Bessel functions. And there are certain open problems on which we are also working, and if anybody is interested, there are like the two variable Q analogs of other special functions, not only the two variable maybe the Q analogs of other special functions. It is mentioned in table 1 that is there are some set relations with some Q special functions or Q analogs of special functions with certain algebras, but it is not limited. but they can be introduced by using the representations of quantum algebras. And also someone may find it interesting to introduce the two-dimensional Q-Hermite polynomials and also related hybrid Q spatial polynomials by using another Q algebra, that is Q oscillator algebra, SUQ11. And many more things can be done as in this conference. There are persons with diverse areas, so there are possibilities, there are various possibilities with maybe with fractional calculus also. I have not tried, but someone can explore that also. So thank you very much. That's all which I want to convey.
Thank you, Subi Madam. This is a very wonderful talk. And I request the audience, if they have any query, can ask from Dr. Subika.
Can I stop sharing or?
Yeah.
Yeah.
Okay, so there is no query?
Yes,
Thank you, madam.
Sir, let me have one question to Subi, ma'am.
Yeah.
Ma'am, can you suggest some immediate applications of this Q analogs? Did you find any immediate applications of the Q analogs in any other area? Means some real life problems. Is there anything like that?
Actually, when we go for, when the word Q comes, it is just like we are entering into quantum world.
Quantum mechanics.
Quantum mechanics or quantum physics. So mostly the applications of Q special functions is in the field of quantum physics or quantum mechanics. But as you know, we were not trained to see the concrete applications, and maybe there is lack of collaboration also. But definitely, if we go through the Q analogs of special functions, there is a vast application, because the origin of Q special function itself is from quantum algebra or from quantum physics.
If you get that original publication for that application, you please send me.
Yes, sure.
I'm already interested in this one.
For sure. Actually, special function, if we look at a special function, this is a very obvious question which have been asked. If we have to think about the applications of special functions or Q special functions, if you look at their origin, they have been born from the applications itself, isn't it? So they have been originated from the physical phenomena.
No, ma'am. Actually, what I was telling is that most of the special functions which we use are already applied in various areas in physics. But that is explicit. But I have never seen that about Q special functions. So that is why I asked this question.
I will definitely share if I get some concrete example, or if there is a literature which can solve your query or which can satisfy your query, I will definitely share this with you.
Dilip, basically, whatever you're working in your field, you can also obtain the Q analog of that.
Yeah.
Q analog of this.
Sir, I have just started thinking over this Q analog, but since I was working in an applied area, so I was thinking that whether it can be applied to simply we can extend, but we should have to give some practical application also.
Actually, that condition, the mode of the Q less than 1.
But if
so
you look at the work of your supervisor, Professor Mathai, there are several books on basic hypergeometric functions and all these things.
No, but Q hypergeometric he has not worked up to now.
Yes.
Q hypergeometric he has not worked. He has worked only special functions, but Q is a different thing. So that is what I was thinking.
This time they are using, in approximation theory, in operators, they are generating operators. Even they have gone for PQ. So Q and then PQ and all these things. So they are using
so many cases are there. Basically.
Yes.
P calculus also the Planck based on the Planck constant. They can use Planck calculus as a Q calculus.
Previously, also Dr. Dilip, I want to share my personal thought with you. When we have started, I have not worked very much on this Q analogs or Q special functions, and I was like, whenever I started working on it, I found it a bit boring. But when I found its relation with this Lie algebra, then I thought that there are certain things which we have to ponder and which we have to think, and then maybe we will be going to see something related to the approximation theory also. So for that, I am there are certain teachers in our department, so we will be trying to collaborate, and if we do, then I will definitely let you know. And thank you very much.
Sure, ma'am. It was a nice presentation.
Thank
You
you.
can refer to the work of Vivek Sahai also.
Yes,
Maybe it's,
yes, he is doing on models, and Professor Manocha lecture, I remember, I think in
Yeah.
Jodhpur. If anybody remember, Professor Achal Manocha, he has given in Jodhpur.
Surat.
No, in Jodhpur also.
Not in Jodhpur. It was in SRM Science Congress, if you remember.
No, Surat Mayat abhi hua tha.
There was a conference I remember, and that time he mentioned, and he like encouraged during my PhD time also. I used to visit him, and like he has motivated me to work on the relation of Q special functions with quantum, because he told me that when the word Q comes, it means it has originated from quantum physics or quantum mechanics.
In fact,
So,
very few people have worked on this.
yes, not much work has been done.
Not
Yes.
much work has been done. So
Yes.
there is a lot of scope in this.
Yes, this is my first paper, and you know,
Okay,
after 2019, 2 years have passed. Now I have started this problem again, and maybe hopefully within 6 months we will be going to do
And
something.
interestingly, the tools that you need, the Q analogs, they already, most of them already exist.
Yes. So it is not difficult. Like if you have the tools, you don't have to develop.
The tools are already available.
Yes,
So,
but the
yes.
only thing which we are facing problem is we are not having the disentanglement identities for this.
Arun Verma sir, Mumtaz
Yes.
sir,
Yes.
Mumtaz sir also did.
Sir, I think the Gaspar Roman book is having a good
Yes,
account
yes,
of this
yes.
Q.
Gaspar Rahman, Bruce Bond
Yes,
book
yes,
also there.
Gaspar Rahman, and there is
Bruce
one
Bond
more.
lecture notes also
Yes.
available. And sisters, this is the Slater's books also, basic hypertrophy.
You can give this problem to one of your students if you have.
I am also thinking for that.
Yes. Because we have to add something, because sometimes, you know, you work for in one direction for 5-6 years, then you start feeling that let us go for another thing.
the presentation session is started.
Yes, sir, it is started. It has started.
So I take over, Dilip?
Yeah. So thank you, Ajay sir, for chairing the session, and I thank Atul Dikshit and Subhi ma'am for their nice presentations, and it was very interesting too in the morning. So thank you, participants, for attending this session. We have already started the sessions 7A and 7B, the paper presentation sessions. So it is already going on. So those who are presenting today may please join that session for presenting their papers. So thank you very much. We will be coming back. We will be coming back at 3 o'clock in the same link for the symposium on special functions and fractional calculus. So Professor Varsha Geji ma'am will be sharing. She will be chairing the session. And we have top researchers like Virginia Kiriakova, Iva Kashlik, and Francisco Mainardi, Sachin Bhalekar are all speaking on this occasion. So it's a nice session.
Okay.
Yes, Professor S.K. Upadhyay is in the room. He has to chair the session.
Yes.
I mean, Dr. S.K. Upadhyay, you may join the session. I think you are chairing the session today only.
Yes. Upadhyay sir is chairing today.
So,
I have.
But he
11:15 2 p.m.
But he is in the room. He should now join there. Professor
Yeah.
Upadhyay, if
Upadhyay
you,
sir, Upadhyay sir, are you there?
yeah, Professor Upadhyay, if you can hear us.
I don't think that he can hear because his audio is muted. I think he is not joined with audio. So I think that he has simply joined.
Because he is in the room. He must join the session now.
Yeah, I will call him, sir.
You please call him.
Okay.
Okay.
So thank you,
Okay.
sir. Thank you,
Thank you.
ma'am.
Thank you. So I'm leaving this meeting now.
Yes.
Yeah.
Okay.
Thank you, madam.
Okay.